important implications of the special theory of relativity is the idea of time dilation. As an object moves at a higher velocity, the time moves more slowly than another object that is not moving. The time is not the only quantity that changes when we change reference frames. Length and distance are also affected. We have our spaceship that is leaving Earth for a distant star. We have an observer who stays behind on Earth. Earth in this case is the inertial reference point and is assumed to be stationary. The velocity of the spaceship, as seen from the person on Earth, is simply the distance it is traveling divided by the time measured by the Earth observer. Now remember that the observer in the spaceship is experiencing time dilation, so the time that passes inside the spaceship is less than the time that passes for the observer on Earth. The velocity of the spaceship, however, does not change. So if the velocity of the spaceship is the same for both observers, but the time passing for the person in the spaceship is less, then the distance measured by the person on the spaceship is also going to be less than the distance measured by the person left on Earth. So the observer on Earth can determine the velocity of the spaceship by taking his measured distance to the star and dividing it by the time he measures the spaceship is gone. L0 represents the distance that is measured by the Earth observer, and delta t represents the time he measures. Since time is what is changing for the observer in the spaceship, we can rearrange this expression to solve for the change in time. We already know that time is passing differently for the observer on the spaceship. We can determine this time with a lovely expression for time dilation. Remember that delta t represents the time elapsed for the Earth observer, and delta t0 represents the proper time, or the time elapsed for the observer on the spaceship. We know that the velocity of the spaceship is constant for both observers. So L is the distance that the person on the spaceship must observe to account for the change in the elapsed time if the velocity is constant. We can rearrange our time dilation equation to an expression that solves for the time elapsed for the observer on the spaceship. From here, we can just plug that expression for our proper time in the expression that we have for the change in length for our spaceship observer. Delta t in this expression represents the time elapsed for the observer on Earth, and we know that this time is equal to the length the Earth observer measures divided by the velocity of the spaceship. Substituting that in, we see that there are a couple velocities that cancel each other, and we are left with an expression for the length contraction as observed by the person on the spaceship. L0 is known as the proper length, and it is the length that is measured by the stationary Earth observer. Notice that the expression under the square root will always be less than 1. This is just an indication that the length observed by the spaceship observer will always be less than the length observed by the person that is stationary. Something else to keep in mind is that not only does this equation apply to the distance the spaceship is traveling, but also the length of the spaceship. So if the observer on Earth were to measure the spaceship itself, it would actually measure shorter when it is in motion than when it is stationary.